All right, good afternoon. I'm Norman Wahlberger at the University of New South Wales, and we are in this course on the history of mathematics. Today we're going to talk about Greek number theory. That means ancient Greek number theory. And we're going to cover a number of interesting points. We're going to talk about some special numbers, including, square numbers, triangular numbers, prime numbers, which are particularly important, and also perfect numbers. We're going to talk about a very important algorithm, the Euclidean algorithm, for greatest common divisors. And we'll talk about Pell's equation and the cattle problem of Archimedes. And maybe I'll say a little bit about continued fractions also. All right, so while the ancient Greeks were mostly concerned with geometry, they also made important advances in number theory. A number theory is really a glorified term for arithmetic. We're really interested in arithmetic with natural numbers. And of course, that's been going on for a long time, much earlier than just the ancient Greeks. But if you do a lot of arithmetic with natural numbers, you start noticing some pleasant patterns, and interesting numbers come up, and it's interesting to study some of these things. The subject is closely connected with mystical aspects. Numbers have often had a almost religious or mystical effect on people. Certain numbers are lucky, certain numbers are unlucky, and so on. And so some of the earlier work no doubt had a kind of a mystical overlap. So for example, some of the first numbers that were investigated are, for example, square numbers. A square number is simply a number that you get by looking at a square, say 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So there's a square number. In this case, 25, which is 5 squared. And one of the things that the ancient Greeks realized is that you could think about the square as being decomposed into a bunch of successive layers. So you could think of this first square here as perhaps the starting point, and then we have an L-shaped region of 3 different squares. They called such an L-shaped region a gnomon. And there's another gnomon with 5 elements, and then another one with 7 elements, another one with 9 elements. And from this we can quickly see that 25 is also 1 plus 3 plus 5 plus 7 plus 9. And that pattern obviously generalizes that the sum of the first odd numbers is always a square. Other numbers that were related to geometry they were interested in. So another kind of number is a triangular number. And we can represent triangular numbers, say, with dots. So 1 is a triangular number, and 3 is a triangular number, because it sort of forms a triangle. And then we could have 3 on base, and then 2, and then 1. So that would be a 6. That's a triangular number. And then a base of 4, base on 3 on top, 2 and 1. That's 10. And we keep going. These are triangular numbers. And they also have another way of thinking about them is if we put them on the side, we can say, look at something like 10 and think of it as being a 4 plus a 3 plus a 2 plus a 1. So there's 10, another version of the triangular number 10, which makes it obvious that it's equal to 1 plus 2 plus 3 plus 4. So the triangular numbers are the numbers which you get by summing up the first n numbers. And a relatively easy formula for that can be obtained by thinking about what happens if you double that. So if I add, maybe in blue here, there's another 1, and then there's a 2, and then there's a 3, and there's a 4. Okay, so this thing here, 2, 3, 4, 1, 2, 3, 1, 2, 1. That's exactly another copy of the same thing. And when we do it like that, we see that this triangular number, which maybe we could call T4, the fourth triangular number, if we take 2 times it, 2 times T4, we are going to get a rectangle. And the rectangle has sides 4 and 5. So 2 times T4 is 4 times 5, giving us T4 equals 4 times 5 over 2. That's not that interesting when T is 4, but it's much more interesting if T is a bigger number because it applies equally. So for example, if you wanted to sum all the numbers from 1 to 100, you recognize, well, that's just a triangular number. It's the same kind of picture, except that it's much bigger. And exactly the same reasoning will tell us that T of 100 is going to be equal to the area of a rectangle of sides 100 times 101 divided by 2. And that's equal to 5050. That's a computation. I think a story goes that Gauss may have done that in his head when he was a young lad in some classroom, and impressed his teacher that he was able to just sort of figure out how to do it without actually having to add up all the numbers. So that's an important formula for triangular numbers. Of course, the general formula is that T of n equals n times n plus 1 over 2. And those numbers are quite important in mathematics. But they still have something of a recreational aspect to them. Much more important for the history of mathematics are the prime numbers. So the prime numbers are those natural numbers with no factors or no divisors other than 1 and themselves. So for example, a number like 18 is equal to 2 times 9 as well as 1 times 18. So this is not prime because it has factors. Factors are 1, 2, 9, and 18. However, 19 can only be written as 1 times 19. Those are the only factors, so this is prime. And the list of primes is both intriguing and somewhat regular, but also somewhat irregular. So 2, 3, 5, 7, 11, 13, 17, 19, 23, 29, 31, 33, 35, 37, 41, blah, blah, blah. Okay? They get a little bit sparser as we get out. There's quite a lot of them between 1 and 100, but as we keep going, they get a little bit more rare. But one of the great accomplishments of Euclid, or ancient Greek mathematics, was to realize that there were an infinite number of primes. So books 7 to 9 of the Elements were concerned with number theory. Books 1 to 6 was more or less geometry, and books 7 to 9 was number theory. And by the way, here's another edition of Euclid's Elements. This is also a famous edition. It's a 3-volume set published by Dover, so it's relatively cheap. And it's got an introduction and commentary, very valuable commentary by Sir Thomas Heath, who was a great Greek scholar and has lots of interesting things to say about it. He interprets all the theorems and gives historical background. Very, very, very beautiful. So I can state a very important theorem that the ancient Greeks realized about prime numbers. The main fact about prime, well, one of the main facts about prime numbers, probably not the main fact. So here we are, proposition 20 of book 9. So it's important, interesting, the statement of it. So let's write it down exactly as translated here in English. Prime numbers are more than any assigned multitude of prime numbers. Prime numbers are more than any assigned multitude of prime numbers. What does Euclid mean by this? Well, in present day treatments, this is usually rephrased in a kind of a modern way. The modern rephrasing of this is that the set of prime numbers is infinite. That would have jarred with the ancient Greeks because they did not like to think in terms of infinite sets. They would rather have said, or the sequence of prime numbers does not stop. It keeps going. So this sequence here does not stop. It's not the case that there is some biggest prime number and that after that they're all composite. This list keeps on going and going and going and going. And the Greeks like to think of infinity as sort of, just keeping on going beyond the view. Keep going, we never get to the end. And his proof is elegant and clever. And what is the proof? Well, suppose there were only a finite number of primes. Let's say P1, P2, up to Pn for some n. Okay, suppose that there were only a trillion primes. Okay, so we're going to try to arrive at a contradiction from this. We've got to try to show this is actually impossible. So what Euclid does is he says, all right, let's consider a new number, a much bigger number. So consider the number, let's call it capital P. Well, maybe I shouldn't use capital P because it's not necessarily a prime. It's suggesting it's a prime. Let's use capital N. Consider capital N, which is the product of all these numbers, P1 times P2 times all the way up to Pn plus 1. The product of all the primes in our list added to 1. This number, n, is not divisible by any prime p, I. Any of our primes, it's not divisible by that prime. Because if you divide it by pk, you're going to get a remainder of 1. It's 1 more than a multiple, so if you divide it by that thing, you're going to get a remainder of 1. It means it doesn't divide. So if you look at the factors of this thing, there are sort of two possibilities. So what are the factors? What are the possible factors? Well, one possibility is that n itself is prime. But that would contradict the fact that all the primes are P1 to Pn, because this is obviously a new prime. It's obviously bigger than all of the numbers P1 through Pn. So this is impossible, since it's not on the list. We're assuming we've got primes P1 through Pn. And the other possibility is that n is composite, but then it must have some prime factors itself. But then any prime factor is a new prime not on the list. So either way, we get some new primes. Either n itself is a new prime, or one of its factors is a new prime. So that's the end of the proof. Now we're kind of using some facts here that Euclid knew. And so the most important fact about primes, the fundamental theorem of arithmetic, it's sometimes called. Well, this also goes back to Euclid, is that every natural number can be written as a product of primes. In essentially one way. So up to rearrangement, or up to order. Okay. This is a very important fact about numbers. Every number can be written as a product of primes. So for example, 612. Okay, if I look for factors, well, it's obviously even, so it's going to have 2 as a factor, so I could divide by 2 and I get 306. Okay, that's still even, so I could still I could now write it as, okay, 2 times 2 times, divide this thing, is 153. Is 153 prime? No, it has some factors. I could divide that by 3. So it's 2 times 2 times 3. If I divide that by 3, I get 51. And 51 is also divisible by 3. If the sum of the digits are multiple of 3, then the number is divisible by 3. So we can write it as 2 times 2 times 3 times 3 times 51 divided by 3 is 17. And now we can't keep going because those are all primes. We've written it out as a product of 5 primes. And if somebody else started with some other way, they would still end up with these 5 primes, but perhaps in some different order. But whenever you factor a number, this prime decomposition that you get is always the same. That's the fundamental theorem of arithmetic. Okay, this is a very important theorem, and the proof requires some careful bookkeeping and requires a bit of preliminary number theory. So we're not going to do the proof, but in a course on number theory, this is one of the first things that you do. There were some other interesting numbers that the ancient Greeks were interested in, and they're called perfect numbers. What is a perfect number? Well, it's a number that you get by looking at all the divisors. So suppose we take a number like 12, and we consider all its divisors. So these are just numbers that divide 12. So they are 1, 2, 3, 4, 6, and 12 itself. Okay. While a number like 7 would have divisors 1 and 7. A number like 6 has divisors 1, 2, 3, and 6. A number like 28 has divisors 1, 2, 4, 7, 14, 28. Now there's something special about 6 and 28. They are perfect numbers, according to the ancient Greeks. Why? So a perfect number is one where a number is perfect if the sum of all its divisors, well, the divisors that are less than itself, all its divisors less than itself, is the number itself. So 6, 1 plus 2 plus 3, all the divisors which are actually less than 6, that equals 6. And 1 plus 2 plus 4 plus 7 plus 11 is 22. Oh, where's 14, not 11? 14. 1 plus 2 plus 4 plus 7 plus 14 is 21, 25, 27, 28. Those are perfect numbers. While 12 would not be a perfect number because 1 plus 2 plus 3 plus 4 plus 6 is 16. That's not equal to 12. That's not a perfect number. And 7 is not a perfect number because 1 is not equal to 7. So the Greeks liked perfect numbers, and they proved a lovely thing, which is actually the culminating theorem in Book 9. So this is perhaps the pinnacle of the Greek work on number theory. So it's proposition 36 in Book 9. And okay, it's a little bit long, but let me state it. I'll read it. If as many numbers as we please, beginning from an unit, be set out continuously in double proportion until the sum of all becomes prime, and if the sum multiplied into the last makes some number, the product will be perfect. Okay, if as many numbers as we please, beginning from a unit, be set out continuously in double proportion until the sum of all becomes prime, and if the sum multiplied into the last makes some number, the product will be perfect. What's he saying? He's saying in modern notation, he's saying if you start off with 1 and you double it and double it again and double it again, okay, and keep going till maybe I'll write it as 2 to the n minus 1. So if this number is prime, then the product of then the sum, okay, the sum multiplied into the last, this is the last, okay, then 1 plus 2 plus all the way up to 2 to the n minus 1 times 2 to the n minus 1 is perfect. Okay, so let's have a look. So for example, 1 is not considered a prime number, but 1 plus 2 certainly is a prime number. Okay, so that's prime. And so therefore Euclid would say, all right, so if you take that sum, 1 plus 2, and multiply it by 2, you get 6. That's perfect. Okay, what's another example? How about 1 plus 2 plus 4? Is that prime? Yes, it is. So that's prime. So if you take 1 plus 2 plus 4 and multiply it by 4, you get 28. That's perfect. How about 1 plus 2 plus 4 plus 8? That's 15. That's not prime. That's not going to work. But the next one is 31. That is prime. So 31 the sum, 1 plus 2 plus 4 plus 8 plus 16 times 16, which is, what is it? So that's perfect. Well, you might say, but wait a minute, didn't the ancient Greeks know about a geometric progression? This is a geometric progression. Right, we know how to sum that. What is 1 plus 2 squared plus 2 cubed all the way up to 2 to the n minus 1? Well, it's the next term in the expansion, which is 2 to the n minus 1, divided by 2 minus 1. The ratio is r. So this is just 2 to the n minus 1. So this number that's appearing here, we could rewrite it more efficiently as 2 to the n minus 1 times 2 to the n minus 1. Well, so we could state it another way, i.e., if 2 to the n minus 1 is prime, then 2 to the n minus 1 times 2 to the n minus 1 is perfect. That's just a restatement of Euclid's theorem. So what numbers of the form 2 to the n minus 1 are prime? Well, that's an interesting question. And those primes are particularly interesting, and they're called Mersenne primes. Not every number of the form 2 to the n minus 1 is prime. For example, 15 isn't. But quite a reasonable number of them are. And when people look for primes, there are certain reasons why these kind of primes are easier to find than others. So finding primes is in fact not as easy as one might think. Euclid's prescription for multiplying a whole bunch of primes together and adding one and then factoring it is impossible if you have already billions of primes. It's practically impossible. So although it's theoretically available, you can't generate new primes this way in practice. And finding ever and higher primes is an interesting undertaking that many people on the internet spend a lot of time doing. The current world record. The world record, at least the site I checked, current world record, I think it was set in 2008. This is the largest prime known. The largest known prime. Largest known prime number is 2 to the 43112,609 minus 1. It's a number with about 12 million digits if you wrote it out. Humanity does not know any primes bigger than that. And there's no easy way of finding primes bigger than that. You have to work a lot, and you have to get your computer to do a lot of work to find any prime bigger than that. As you can see by the fact that it's already, been a couple years and people haven't improved on it. This kind of number theory was, for many centuries, considered a sort of a frivolous entertainment and only a sort of abstract game for mathematical types. But in the last few decades, this kind of thinking about primes has become very important with internet and security issues. So these days we have encryption methods to encrypt your bank details when you send them on the internet. And these bank details are encrypted by some number theory that rely often crucially on prime numbers. Okay. And so one property of prime numbers that's kind of crucial here is that using primes, you can find out a fact that nobody else can find. That nobody else can. All right, so you could do this. So how do you find a fact that nobody else can crack? The fact is, what you do is you go to your favorite program like Maple or MATLAB or Mathematica. These are programs that help us do mathematics. And you churn out a command that's something like this, next prime, and then you write down some rather random number. Okay, so if I type that into Maple and click it, then within half a second later, it will tell me what the next prime is after that. So Maple has no problem finding the prime which is bigger than that one, the next prime bigger than that one. So I could do this twice. I could take this and then I could take next prime of some other number. Okay, so now I've got two primes, P1 and P2. And now I multiply those two numbers together and I offer $1 million reward for anybody who can factor that number. And if I've chosen these numbers reasonably big, then you're not going to be able to factor that number, even if I advertise it. I'm going to be the only one, or you're going to be the only one, who knows what the factors are. They happen to be P1 and P2, which you've written down on a piece of paper. But nobody else can figure that out, even if they work hard and use all kinds of computing power. And it's that fact that there's something that you can know that nobody else can know that is the key to encryption. That you can exploit that to send secret messages and to decode them. So prime numbers are, in fact, quite important these days, and worrying about big numbers, worrying about big primes, worrying about factorization, it's something that security analysts and military types are very interested in. But now I want to tell you about a very important Euclidean algorithm. Suppose we have two numbers, and we'll just illustrate this with an example. Suppose I have number 612 and 93. Okay, I've already told you that 612 is 2 times 2 times 3 times 3 times 17. And we could factor this one. This is 3 times 31. So, two somewhat random numbers. And here are the prime decompositions of these numbers. What is the greatest common divisor? The greatest common divisor of 6, 112, and 93 is the largest number, the largest common divisor. It's a number that divides both of them. That's as big as possible. Now, in this case, it's easy to see what the greatest common divisor is, because we just look through here and see, well, they have 3 as a common divisor. 2 is not, 31 isn't, 17. So in this case, this will just be equal to 3. That's the biggest divisor that they both have in common. But suppose I asked you to find the greatest common divisor between these two numbers. If you wanted to try this idea, you'd have to factor these numbers into primes first. And that might be very, very hard if you don't have a computer with you. A computer would factor these very quickly, but you by yourself would have a hard time doing that. And before computers were around, how would you find the greatest common divisor of two big numbers like this? Well, that's an important problem that the ancient Greeks thought about, and there's this very important algorithm that Euclid devised. Okay, and here's what you do. So here's the algorithm, and we'll just demonstrate it on 6, 12, and 93. So it's one of the first cases of an algorithm, of a sequential step that actually accomplishes something in a very logical, systematic way. We take the biggest number and we divide it by the smaller number. Okay, so you divide it and you're going to get a remainder. So 612 is equal to 6 times 93 plus a remainder of 54. And now the key observation is we started with this number. And with this number, these are the two numbers we started with. We want to know what their greatest common divisor is. The key observation is now that the greatest common divisor is going to be the same as the greatest common divisor between these two numbers. Any number that divides these two is also going to divide this one. Like if this one's divisible by 17 and this is divisible by 17, then 17 will divide this whole right-hand side, and so it will divide this. So the problem of finding the greatest common divisor is now reduced to a smaller problem, namely the problem of finding the greatest common divisor of these two. That's the same problem, but with smaller numbers. So we're just going to iterate. Okay, what was it that we were doing? We were taking our number and dividing it by the other one. So 93 divided by 54 is 1 times 54 plus 39. Okay, now the greatest common divisor between 93 and 54 is the same as the greatest common divisor between these two. Same argument. So we repeat. We divide 54 by 39. We get 1 times 39 plus a remainder of 15. And then we divide 39 by 15. 2 times 15 plus a remainder of 9. And then 15 is 1 times 9 plus a remainder of 6. And finally 9 equals, maybe not finally, 1 times 6 plus a remainder of 3. And finally we get to the stage where 6 is equal to 2 times 3 with a remainder of 0. So the greatest common divisor between 6 and 3 at this stage is 3, because 6 is a multiple of 3. Once you have a remainder, it means that 1 is a multiple of the other. And so the smaller number is the greatest common divisor. So this last remainder that we got, that is the greatest common divisor. So that's perhaps the world's first algorithm, and it's a much more efficient way of calculating the greatest common divisor of two big numbers rather than factoring them. All right, we'll take a break there.